Okay. Good. Okay. Okay, I think it's time. It's good to see a lot of people. Fridays are a bit lonely here. I hope to see more of you during Fridays. Okay, today we're going to continue what we started in the last lecture, which was multi-cycle processor design. Remember, we're still covering microarchitecture. We have been designing the microarchitecture of a very simple MIPS processor for the last couple of lectures. And we decided single cycle processor design is not a good idea. It violates three major fundamental principles, which we will very quickly get to today, just to jog your memory. Today, we're going to design the full multi-cycle processor, well, full for a subset of the MIPS ISA, following your book. There's more in your book that talks about it. And then we're going to jump to pipeline processors, which are actually the type of processors that we have today, but we'll actually build on pipelining also. Okay, you have an assignment, extra credit assignment due if you want to get extra credit, April 1st. And this is where we are. I kind of covered all of this. My goal by the end of this week is to finish pipelining. We're going to cover a bunch of issues in pipelining. And then next week, we're going to talk about state maintenance and recovery, precise exceptions, and out-of-order execution. Does that sound good? Okay, yeah. By the end of next week, you will know how a modern microprocessor actually processes instructions in an out-of-order manner. We're just building up to it right now. But we need to build up to it because you need to see what is data and control dependence handling, what's pipelining, etc. And these are some of the readings. For multi-cycle microarchitecture, I'm going to follow H&H, chapter 7.4, which actually does a good job, I think. Pat and Patel appendices, especially Appendix C, builds a full LC3B microarchitecture. It's a very good one. I'm going to briefly talk about it, but if you're really interested in looking at it, I would suggest looking at it because that gives the concepts very nicely. And then we're going to talk about pipelining. Okay, multi-cycle. Just to recall, basically our goal with multi-cycle microarchitectures is to let each instruction take only as much time as it really needs, as opposed to the worst case instruction determining the clock cycle time as it happened with single cycle architectures, right? And this is kind of the pictorial view. You have an architectural state at the beginning, and every clock cycle you do something and update some microarchitectural state to process an instruction until at the end of the instruction you finish the processing and you update the architectural state. So we can use multiple clock cycles to process every instruction, and you can use different number of clock cycles to process different instructions, and you can determine the clock cycle time independently of how long it takes to process any instruction. And we said that you could do this by building a state machine, and we're going to build that state machine today, a small version of it. And this was the full state machine for LC3B that we partially covered, but we're going to build a new one, not for LC3, for MIPS. And this is the LC3 multi-cycle implementation. If you read Appendix C, you will see a lot of this. Okay, so basically, these are what we aim to accomplish with multi-cycle design. We want to have better critical paths, reduce the clock cycle time. We want to optimize the finite state machine for the important things that we want to execute. For example, the most common workload, most common instructions. And we want to have a balanced design. We don't want to provide capability no more than that's really needed. Okay, you have already seen these, but this will come at an expense. As every idea, there's an upside and a downside. If you find some, if you're given an idea and you want to analyze it, always look for the upsides and the downsides. There's nothing without an upside. There's nothing without a downside. Upsides or downsides may be different in terms of weight, but they exist. Okay, so in this case, we're going to need to store the intermediate results at the end of each clock cycle. And we're going to pay both the hardware overhead for that as well as a sequencing overhead, meaning we're going to waste part of every clock cycle as we've seen in timing and verification. And we're also going to see that we're going to have limited concurrency, and we're going to solve that problem partially with pipelining. Does that sound good? Okay, so you've seen all of this, and this is the slide I stopped at last time. Basically, we wanted to have a closer look at a multi-cycle microarchitecture. This is actually an idea that was developed by Maurice Wilks, who is a pioneer in the field of computer architecture and computer microarchitecture. And he developed the concept of micro-coded microprogram machines that we're going to see soon. But a lot of these concepts are based on his descriptions. Okay, so basically the key idea of realizing a multi-cycle microarchitecture is to see the process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. So you keep doing this. So you have a finite state machine that implements your entire ISA. A state is really defined by the control signals asserted in that state, basically. And control signals for the next state are determined in the current state, so that we can parallelize processing. We don't need to waste part of the clock cycle for determining control signals. Make sense? We've discussed a lot of these actually. So now we're going to implement a basic one. So we're going to, you've seen actually a lot of these concepts, so hopefully a lot of these are familiar, but the implementation will be similar to what we have done with single cycle. We're going to start from a basic instructions, and we're going to start from the data path, and we're going to start adding things to the data path. But essentially, we're going to see instruction processing cycle to be divided into states, and each stage in the instruction processing cycle can take multiple states. And we're going to sequence from state to process an instruction. That's what a finite state machine is, right? And you've seen this a long time ago in these lectures. And the behavior of the complete machine in a state is, the behavior of the entire machine in a state is completely determined by the control signals asserted in that state. Similarly to the control signals we had in single cycle that essentially determine what the data path elements are going to do to the data and the instruction, etc. We're going to do the same thing. Control signals are going to determine everything in that particular state. And the behavior of the entire processor is specified fully by a finite state machine. So in a state or in a clock cycle, control signals control two things: how the data path should process the data, as we have seen in the past, and how to generate the control signals for the next clock cycle. And this is what we have seen. So let's build another example multi-cycle microarchitecture. I'm going to follow your book. So if you're interested, you can look at your book. I don't remember if it's 7.3 or 7.4. Maybe someone can verify this. Maybe the figure is in both places. I thought it was 7.4, but this says 7.3, so there might be a bug over here. Anyway, but this is a multi-cycle machine that is built by your book that supports a subset of the MIPS instruction set architecture. Oh, actually, this is the single cycle microarchitecture. Sorry, this is correct. This is a single cycle that we developed in your readings. So what is the issue with this single cycle, right? So we're going to build chapter 7.4 from here. So in the single cycle, we already discussed this a lot. So cycle time is limited by the longest instruction. You have low clock frequency. But we also said you have a lot of adders and ALUs and memories. This gives you high hardware cost because you have to provide all of the combinational resources to process a single instruction, a given instruction in a given clock cycle. If a given instruction needs to access memory twice, you need to provide the resources for that. If a given instruction needs to do multiple additions, which many instructions need to do, they need to increment the PC, for example, by 4. They need to do an addition. They need to do something else. You need to add adders all over the place, right? You cannot reuse the same adder. In a multi-cycle, we fix these problems. You get a higher clock frequency. You get simpler instructions that taking only a few clock cycles, and you can reuse expensive hardware across multiple cycles. So I'm going to show this when we build the data path. But of course, we know the downsides also. I'm not going to repeat that. So when you want to design a multi-cycle microarchitecture, you go through the same steps as single cycle. What did we do in the single cycle last week? We basically designed a data path, right? How did you design the data path? We took every instruction. We said, okay, let's start with R-type instructions. Let's build a data path for that. And then we added I-type instructions. And then we added load instruction. And then we added store instruction. And then we added branch instruction. And then we added jump. And then we stopped there because you could keep going forever doing that. You do the same thing, basically. You design the data path, you add the control signals, and then you design the control logic. So there's no magic. You follow the same steps to construct a multi-cycle processor, except it's a multi-cycle processor. It's not a single cycle processor. Okay, so what do we optimize? Of course, when you construct the data path, you need to think, meaning what am I going to do in my data path, right? Now I can optimize things. As opposed to using 2 memories, we can only use a single memory, and we're going to see that. It's going to be much lower cost. As opposed to using 3 adders, one for ALU, which you need, one for PC incrementing, and the other for branch address calculation, we're going to use only 1 ALU for all operations. And this is going to lower the cost again. As opposed to having each instruction take 1 cycle, we want to determine the clock cycle independently of instruction processing time. So when we actually design the data path, plus the finite state machine, we're going to divide each instruction into multiple clock cycles. Okay? Makes sense. Okay, so let's construct the multi-cycle data path. In this case, we'll start with a load word instruction, because why not? Last time we started with an add instruction. Why did we start with an add instruction? Why not? Basically, there's no real reason to pick one instruction over the other, because in the end, you're designing a data path for all instructions. And if you're going to execute all instructions, you might as well start with some random instruction also, right? And it's also good to think about, okay, maybe you start with common case instructions, right? Maybe why not is not the best answer. A qualified answer is, which instruction is going to be the most important one for me? Loads, adds, those are pretty common instructions. So you can start with those without any, let's say, downsides. So remember the load instruction. Essentially, what this load instruction is, it has a destination register. It has a source register. Essentially, it computes the address by taking the source register, adding to it an immediate, sign extend immediate, and reads the content of the location in that memory address, and then gets the data and puts the value into the destination register. I'm not going through the encoding, etc., because we've seen this, but the encoding is kind of here. It's an I-type instructions in MIPS. Essentially, fetch is really the same for all instructions. For load, step 1 is really fetching the instruction. But to construct the data path, you need a program counter. You supply the program counter to the memory that we have seen before, if you remember from earlier lectures. You input the program counter to the address port of the memory, and then you get the data from the output port of the memory. And this data is really your instruction, and you're going to latch it in an instruction register. We're going to call it the instruction register write signal to enable, or write enable this register. So we added 1 control signal here. There's another control signal here, which is the write enable of the memory over here. And we have 1 memory to begin with. Does this make sense? So this is our first cycle, essentially. And first cycle is defined by the control signals associated with it. IR right should be 1. All other control signals over here should be do no harm. We have not constructed that yet, so we're going to build the control logic later. Okay, so that was the fetch. That was easy, clearly. Clearly, this is common in all instructions. All instructions do this. Okay, so the second step is to read the register. And the way we do it is essentially you take some bits from the instruction over here, which is one of the source registers. We're going to calculate the address using that. This is the base register, if you think about it. That's 26 through 21. Supply to the register file and get the data out of the register file from the first port, because we supplied to the first port, and latch it into a pipeline register over here. So we're essentially adding registers, as you can see, so that at the end of a clock cycle, we can store the output of what happened in that clock cycle. So that's the difference from the single cycle. We have not constructed the entire thing. We are actually doing it step by step. Of course, you need to also determine what to do in a cycle, but I'm assuming these are the things that we determined to do in a cycle for now. Okay, so you need to assert the control signals to enable this, which are not that many actually. This is register files automatically enabled. There's no write enable. You need to do no harm to the register file at this point when you're actually reading a register for load, etc. And of course, I'm not connecting other things that I don't need for now, but we're going to use them later on. Okay, so load word actually, what load word does is it takes a register, which we actually latched over here in this. It takes a general purpose register, base register, which we latched over here. Concurrently, you take the bottom 16 bits of the instruction, sign extended, and that's going to be our sign extended immediate value that we're going to add to the base register. But we're not ready for that yet. For that, we need another cycle. The next cycle, we basically take whatever was stored in this, let's call it the A register file, A port register, send it to the ALU through a wire, and send the sign extend immediate to the ALU, and set the ALU control bit to do addition, because we do base plus offset, if you remember. And the ALU result will come out, and you store it into this register now. This register is going to be the ALU output register, okay? So that's our third cycle. So one cycle, fetch. The second cycle, register read. Third cycle, generate address. We're not done yet. We generated the address. What do? Now we're going to do something that we cannot do in a single cycle architecture. We're going to basically take that address, loop it back into the address port of the instruction/data memory, and we're going to select that one in this cycle so that we actually access the memory with the address that is generated by the load instruction in this particular state, okay? So earlier in the fetch state, we used the program counter to access the memory. Here, we want to use this address that we calculated to access memory. So we need to add a multiplexer for that, and we need to add a control signal to control that multiplexer. Basically, are we doing an instruction access or a data access? Makes sense, right? Okay, now you can get away with using a single memory, as you can see. That's the beauty of multi-cycle architectures, one of the beauties. Okay, I think I've said this, but of course, you cannot use this memory for both instruction fetch and also data fetch in the same cycle. You can only do instruction fetch in one cycle and data fetch in some other cycle, right? And you control, how do you know what you're doing? Control signals decide that. What are the control signals determined by? They're determined by the control logic, which are based on which state you're in, okay? Okay, so now we read the memory. Oh, okay, this is the address that we input into memory. We get the data after some point. We latch it in a different register. And that data is going to go to the register file in the final state of execution of the load. You basically take this data, put it into the data input port of the register file, and you take this register identifier, which is a destination register identifier, 20 through 16, RT, and essentially you assert the reg write signal, because at this state, we're going to write this data that we latched in the previous cycle to this register ID, because we are asserting the register write signal. And because that's what we're supposed to do at the end of the execution of the load, right? And that finishes the execution of the load. That's the entire data path you need to execute the load. Not really. We forgot to increment the PC, right? Okay. So we're almost done basically with the load. This is what happens with memory access, writing the data register, address calculation, etc. It took a number of cycles, as you can see. Now let's also increment the address. Now your book does a fancy thing. That's why I follow your book. It basically shows that you can use the same adder, ALU, that you used to calculate the address in a previous cycle to also increment the PC. So how do you do that? Basically, you take this program counter, go through here, add another multiplexer over here, because we are going to input the program counter into the ALU. Earlier, we input this register into the ALU. So you select between the program counter or the register. So there's an ALU source A multiplexer. There's also an ALU source B multiplexer that got expanded a little bit more than load needs over here, which is fine because it's going to be needed by other stuff. But basically, source B can come from this register, which we're not used yet. But now we need 4. Well, we use actually sign extend immediate. So we can select between sign extend immediate or 4. Oops, sorry, what happened? Okay, increment PC. Basically, this ALU source selects PC, which is 0. This ALU source B selects 4, because we are going to do PC plus 4, and ALU control should be set to addition over here. And we take the ALU result and put it into program counter. So we need a PC write signal to write enable the program counter register. So to be able to increment the PC, we jumped through a lot of hoops because we didn't want to add another adder. Right? This is a design choice that the designer of this processor made. I wouldn't make this choice, and LC3B designers didn't make this choice in Appendix C. If you look at it, they basically have an incrementer for the PC. That can be done concurrently with everything else. Because of this design choice, essentially PC can. There's more complexity over here. But this is a design choice. It's a perfectly valid design choice in the end, right? They avoided adding an adder. Make sense? Okay, so it's beautiful, right? As you can see, you can get away with a single adder. Okay, as long as you control it so that you do the right things at the right time, right? And don't forget to increment the PC. Okay, that was load. Now we're done with the load. But load actually enabled us to fetch an instruction, decode an instruction, and also increment the PC. So we don't need to add any of those 4 other instructions now. Let's take a look at store. For store, we know how to access memory, right? Okay. Basically, what we need to do is we do everything very similar to the load, generate the address, but at the end, we need to actually access another register, which is the store data register, using bits 20 through 16, and also store it somewhere. When we actually access the base register, we also access this register, and then get the data value and write it back into memory at the specified address when the address calculation happens at that cycle. And we need to assert the mem write signal. So this is very similar to what we have done with single cycle. We moved from load to store, if you remember over there. Similarly, we have the entire data path almost. We just need to read another register, which is going to be the data that's to be written by the store to the memory. And we need to provide the data path element and storage for that, this register. And then we need to take it and write it to the destination, to the memory at the address that is computed the same way the address of the load is computed. I'm not going to compute the same address, but you already have the data path elements and essentially this address, right? Yeah, the ALU result, that address over here. You just need to assert the mem write signal and do the IORD signal accordingly. Okay, so store word is very similar to load, except you write to memory. Sounds good? Okay. Now let's look at R-type instructions. So this was store word. R-type changes the pipeline a little bit. Again, I will not go through the entire thing because otherwise it will take forever. But basically, you need to read from both registers, RS and RT. And also you need to write to RD, destination register. So to enable this, so what does R-type instruction do? R-type instruction actually reads 2 registers, these 2 registers in this particular case. So we already have the data path elements because of store actually. And then we send the second register to the ALU also. Store didn't need that. In store, the second register goes to memory. Here, we're doing basically add R1, R2, store the result in R3, for example. So we get one register over here into the ALU, the second register over here into the ALU. And at that state, you do the calculation, store the result in this register. Now, at the write back stage of this part of an R-type instruction, we take the result in the ALU, and we need to put it into the register file. So before, we were actually doing something else into the register file, right? This one was coming. Load was loading this data into the registers file. So you need to add this multiplexer to decide. And this multiplexer is very similar to the mem-to-reg register that we have in a single cycle design. If you remember that mem-to-reg register, you either take the ALU output and put it into the register file, or you take the memory output. It's essentially the same register that you have. Well, same multiplexer that you have, except it multiplexes between this register and this register, okay? One register stored the data that we read from memory in the load instruction, and the other register stored the data that we calculated as a result of the ALU operation, okay? And then we already had this mux in the single cycle architecture also because of the specific encoding in the ISA. In R-type instructions, remember, the destination register is really, I think, 15 through 11, as opposed to 20 through 16. So you need to select 15 through 11 as your destination register. In I-type instructions, it's 20 through 16. This is based on the encoding. So it's very similar to what we had. We just need to build the data path again. Sounds good? Okay. So let's do branch. Branch is going to be also interesting over here. So you need to provide support for two things over here. One is target address calculation, and the other is branch condition calculation, right? And we already have most of this. Now, the interesting thing is your book uses the same ALU to do both the branch condition calculation as well as the target address calculation. This is also another design choice that Pat and Patel book makes differently. They have a special adder for branch target address calculation. Here, everything goes through the ALU. So let's first figure out how to calculate the branch condition. Remember the BEQ instruction in MIPS ISA? It checks whether two registers are equal, R1 and R2, or R source 1 and R source 2, whether they're equal. So you read these two registers. They're stored in A and B. We already have the data path elements for that. You check whether they're equal. So ALE control is set to subtraction, for example. And then there's a signal coming from ALU now saying whether it's 0. That means they're equal. This is asserted if they're equal. Branch is asserted when you're executing this instruction. So if they're equal and branch is asserted, then this is an OR, PC is enabled. And then you can write to PC whatever you compute in a cycle. So this is assuming that ALU can do a lot of operations, as you will see. Yeah. So basically, the calculation of the branch is done this way. Okay. Yeah, calculation of the branch is also done through the ALU in your book. Basically, the way you calculate the target address is you take PC plus 4, which was stored over here at some point. So based on the design of the finite state machine, you already stored PC plus 4 in your PC. You take that and you input that into the ALU in a different cycle. You need to do that in a different cycle because otherwise ALU is doing this computation, also that computation, or you actually have two ALUs, or you replicate the capabilities of the ALUs. But you basically take PC plus 4, add to it the sign extended, immediate left shifted by 2. You select the right things, of course, with these two multiplexers, and then take the ALU result, and that gets lashed over here, and that ALU result gets input into the program counter by selecting the right PC source. Okay? Make sense? So you can use this data path, but you need to make sure these actions are done in the appropriate cycles. So there needs to be a finite state machine that says, I'm calculating the branch condition in this cycle and storing it here. And then I'm calculating the target address in the ALU in this cycle and storing it here. And then you actually do the update of the PC after all of this is done. So there needs to be an orchestrator, which is really the control unit, that goes through the states. Every state by state, sets the appropriate control signals to make sure that this data path does what we want to do. But with this data path, you can actually do it. Okay, and this is the complete multi-cycle processor in your book. Again, your book goes through this similarly to what I did. If you're interested, you can study it. now what we have done is we've added a bunch of extra registers. So these registers did not exist in a single cycle design. Now the upside is we have only one memory and only one ALU and adder. So your book kind of stretched the limits, and with only one ALU, it did things. But of course, if you have only one ALU, maybe you increase the number of states that you have in the finite state machine for different instructions, right? Because when you're doing PC plus 4, you cannot do something else. When you're doing branch condition calculation, you cannot do a target address calculation, right? Okay, hopefully that makes sense. Okay, now let's construct the multi-cycle control logic. We have constructed the data path. We have added the control signals. These blue things are the control signals in this case. Now we can construct the control logic. I'll go through the control logic relatively quickly, but essentially we're going to construct the finite state machine. This is going to be our controller. We're going to supply the opcode to it, and there will be a finite state machine that determines all of these control signals, including the ALU operation. There's also funct, if you remember, in MIPS that determines what the instruction should do. I'm kind of ignoring it because we kind of covered it earlier. But these are multiplexer select signals and also register write signals, register write enable signals. Okay, so let's start with fetch. We've already seen this actually, but you need to do this after you design the complete data path, of course, because you need to make sure you set every control signal to an appropriate value. So in this case, so fetch looks like this basically. I or D needs to be 0 so that we select program counter and input it into the instruction register address port, memory address port. We don't write to memory, so mem write should be 0. Clearly, IR write should be 1, meaning we're going to write to the instruction register, and we're going to update the program counter, so that should be enabled, meaning PC write signal over here should be 1. This is not a branch. When you are fetching, there's clearly not a branch, so that should be set to 0. And PC source over here should be set to 0, so that we get, we essentially, let me see. Yeah, we essentially set the ALU result over here, right? Okay, so basically, this is the fetch state over here. You're fetching the instruction, and you're also incrementing the PC, right? Because incrementing of the PC happens this way, as you can see, right? You basically take the PC, which was here, and you add to it 4, and you get that into the PC. So the control signals are needed to access memory as well as increment the PC. So what are the increment the PC control signals? One is ALU source A. This multiplexer source should be PC, as we have discussed earlier. ALU source B should be 4, as we discussed earlier. ALU operation should be add 0, 1, 0. That's the code of add. And we should take the ALU result over here and send it to the PC. And PC write is already enabled. Does that make sense? So that's the fetch state. You need to do this for every single state, which clearly we're not going to do because we don't have time. But there's no magic over here, as you can see. And your book is not complete because it doesn't list all of the control signals over here, but you can actually figure out the control signals on your own. Okay, so that's fetch. We fetch the instruction, it's in the instruction register right now. Now we go to the decode state. Decode state actually is relatively simple. You basically read the registers because it doesn't do any harm, assuming it's needed. And you basically don't do anything in the decode state. In your book, decode state is kind of empty, except do no harm, of course. Meaning we don't write to any register except for this one, but this doesn't have a write enable signal anyway, okay? Basically, we always read from the register file according to this design. Okay, so the next state, let's assume that the opcode is load word or store word. We jump to this state. Both of them go through a memory address calculation stage clearly. So we kind of consolidate the finite state machine for both of them in the same state over here. So this is the address calculation stage. We set ALU source A to essentially come from the register file, base register. ALU source B to 1, 0, which is sign extend immediate. And we set the ALU operation to add. And essentially the results get stored over here. There's no write enable signal needed for this. So you can see now we're actually using the data path by setting the control signals accordingly. And all of the other control signals are set so that we do no harm. For example, we don't update the program counter. We don't update the instruction register. That would be terrible because we're processing this instruction, right? We should not update the instruction register until we're done with this instruction. Some of these are X's, as you can see. I don't care because you're not updating the memory, for example. I don't care what I do with it. I'm not updating the program counter, so I don't care what this multiplexer selects, etc. So it's very similar to what we've done in the single cycle, except we do it now state by state by state, okay? Okay, so this is the complete load word state machine. Again, I will not go through this, but you all, after this, if the operation is load word, you go to a memory read state. And memory read state basically has some control signals that you can also select, and I'd recommend you doing it on your own if you're interested. I or D needs to be selected to be 1 so that you actually get the address from the ALU output, just like we have built the data path. And then you go to a memory write back state, meaning you write back the data value that you get from the memory into the register, just like we built the data path, and you set the control signals accordingly. This is the complete load word execution. 1, 2, 3, 4, 5 cycles, as you can see, 5 states in the finite state machine. But we also played some tricks to merge states, as you can see, right? We decoded, and then we said if the operation is load word or if the opcode is load word or store word, we jump to the state. And then if we're in this state and the opcode is load word, we jump to the state. So there needs to be some sequencing logic that basically determines which state you go to from this current state. And we've already seen that in the finite state design, right? Finite state machine design. Okay, store word. Essentially, after calculating the memory address, if the opcode is store word, you go to a mem write state, if you will. And here, I or D is set to 1 again because the address is coming from essentially, address is coming from here, not from here, not from the PC. It's coming from the ALU result. And we set mem write to be 1. So that we can write to memory, right? Here, mem write is not set to 1 when we are reading from memory. And then store word doesn't have an extra state because store is done after you write to memory. There's nothing you do with the registers after that point, right? So store word takes 1, 2, 3, 4 cycles. Okay, now we could keep doing this for all instructions. So if the op is R type after decoding, you go to an execute state. You set the appropriate signals in the ALU so that ALU gets the right inputs. And you set the ALU op, etc. And then after the ALU generates the result, you write it back to the destination register by going into another state, right? So you set the control signals accordingly, just like we did. So I'm not going to do that again, but you can convince yourself that this works. Okay, that was R type. And then there's BEQ over here. BEQ is a little bit more complicated, but you can also do that, but I'll leave that to you. So there's only one state over here that enables BEQ. And in BEQ, actually, there's one trick that your book plays. It determines the branch condition over here, which is interesting over here. It determines the branch condition over here, and then it basically calculates the target address over here and updates the PC using that. So this is all done to determine the branch condition, so that you can actually, essentially, if you can look at it, it sets ALU source A to 0, which is the updated PC already, because we updated the PC in the fetch state, if you remember. ALU source B to 1, 1, which is sign extended, immediate, left shifted, ... and basically it does an addition in the ALU or something like that in your book. And then in the next cycle, it determines actually, is that true? Yeah. I think it does it one way or the other. Probably it actually first determines it first it calculates the target address. That's what it does first, and then it calculates the branch condition. Okay, this makes sense because if you look at these control signals, this is really calculating the target address, and these control signals are actually checking whether the branch condition holds if 2 registers are equal, and if that's the case, then you take the target address that you've calculated and place it into the program counter. Okay. Is there a question? Okay. No, yes, question. I cannot hear you very well. Can you speak up? Yeah. So we store it, right? We store it in the instruction register. So it's here. Yes. Slide 40, okay. Let's go back. So we store it in the instruction register, right? This is the instruction register. And you never update it, yeah. That's why, yeah, you cannot do this in a single cycle machine. In a single cycle machine, there is no instruction register, right? But yes, the instruction bits need to remain. Everything that you need to use later needs to remain. That's why you need to store them in registers. Okay. Sure. Okay. Okay, great. Okay, so that was BEQ. Now we didn't do I-type instructions, but I-type instructions like add I, you can also add it over here. They require control signals. Again, you can go through it and figure it out. Basically, this is the construction process. To do jump, you need to extend the data path a little bit. Your book has this nice description that, okay, if you want to do jump, you extend the data path slightly. So how does jump calculate address, if you remember? We take the bottom, I guess, 26 bits from the instruction register and left shift it by 2 and then extend it and then add it. Yeah, I think we'll need to, yeah, basically concatenate it with the PC. All of these are done in this logic. And then you basically update the program counter. So there's another way of updating the program counter, which needs to extend the multiplexer. And also needs an extended control signal for the PC source. We did this actually in the single cycle processor as well. But if you want to add instructions, you essentially need to add data path elements and also new control signals potentially, okay? And then you actually need to change the control signals that you've done over here. So if you forgot an instruction, for example, no worries. You just need to add the data path elements, add the control signals, and make sure all of those control signals are updated in all of your states accordingly so that you do the right thing. So that's one of the other beauties of this machine in the sense that you can easily modify things. This sort of structure, finite state machine, enables you to modify things easily. Okay. Okay, so basically this is the construction. Maybe I took a bit more time than really I wanted to on this topic, but we construct a multi-cycle MIPS architecture right now. Which is a similar process to constructing a single cycle architecture, but it's a little bit different because now we break things into multiple cycles. So this was our single cycle MIPS architecture, microarchitecture, and this was the thinking over there. And this is our multi-cycle MIPS microarchitecture. They look very similar, but now we have a lot of registers to store things, like the instruction register pointed out by your fellow student. And if you want to learn more, chapter 7.4 does a nice job over here. So I'll ask you one question. One of the issues over here is it assumes something about memory. And this is what we have assumed in single cycle also. We assume memory takes a single cycle. Right? Actually, memory doesn't say single cycle. Memory takes multiple cycles. So there are some memory read states, for example, memory read over here, memory write. Even here, fetch. We assume memory takes one cycle, right? So how do you actually accommodate multi-cycle memory? Basically, it's very easy in this design, actually. If your memory has a signal saying that I'm not ready, I didn't supply you the data yet, then stay in the same state, right? You need to be a little bit more careful. You don't want to update the program counter multiple times. There's a danger over here. But you need to stay in the same state. If the memory is not ready over here, stay in the same state until the memory provides the value, right? So this is a conditional change of the state again. Yeah, I already said this. And memory needs to provide some bits or input to the control logic that determines the next state. And actually, you've seen this kind of before when we looked at LC3. There's a memory access state. And if you look at this memory access state, you wait for memory until the memory is ready. If the memory is not ready, this is not R complement, you stay in the same state. If it's R, then you go to the next state, right? Another memory access, another memory access, another memory access. So there are a lot of memory accesses that you do in a real instruction set architecture, and you do the same thing in all of those. So that's a more realistic way of doing it. Your book kind of assumes that, okay, it's one cycle. Okay, this is something I will not go through, but I will recommend people to look at the book, Appendix C for Pat and Patel. Basically, very quickly, what they introduce in that design is slightly different. The principles are the same. It's multi-cycle, etc. but it's also a little bit more structured. Now, let me quickly describe what it is. Essentially, you have control signals. It's a microprogram design. Again, I will not build this. I will not go through this in detail, but I'll give you the key idea. You have control signals associated with the current state. They're called a micro-instruction. And the act of transitioning from one state to another is that requires determining the next state and the micro-instruction for the next state. This is called micro-sequencing. And there's a control store, which stores control signals for every possible state. It's like a small memory. It stores the micro-instructions for the entire finite state machine. You can think of it as like a program. And microsequencer determines which control signals will be used in the next clock cycle. In a sense, what we're doing as hardware designers, after we design the data path and the control signals, and if you think about it this way, you're microprogramming a machine. You're not programming it in the ISA level, you're programming it at the control signal level. And the program is really stored in that finite state machine. Your finite state machine describes your program, and your control store stores your program, and you sequence from micro-instruction to micro-instruction. And each micro-instruction determines the control signals in each state. Now, if you think about it this way, it becomes very interesting, right? We're programming a machine at the very, very lowest levels. It's called microprogramming. And this actually enables a lot of interesting things. So this is what Patan Patel book shows. You have a microsequencer that determines the next state, address of the next state, and essentially address of the next instruction. You can also think of it that way. Address of the next micro-instruction. You access using that address the control store, which gives you the micro-instruction, which are the control signals that you will use in the next state. And that micro-instruction is supplied to the data path so that you do whatever you need to do in this state. And while the data path is happening, you also micro-sequence to the next instruction, right? And this is the full system over here that they design, including memory and I/O, which is pretty powerful. Okay, I think essentially the control signals for the current state control processing in the data path, as well as generation of what's the next micro-instruction to process. And data path and microsequencer actually operate concurrently. I think I already said this, harped this on multiple times, so I'm not going to ask that question. But this is for your own study. It's beautiful. I will not cover this particular slide. You can find it in Appendix C. But you will see that there is a control store. This is actually the program. This is how you program the control signals of a machine. Each entry in the control store is a micro-instruction corresponding to the finite state machine state. And you actually use the address of the finite state, address of the state, or address of the micro-instruction to get the relevant micro-instruction. Before I conclude, let me say a couple of things. So this makes the data path very powerful. Why am I telling you this? So you can actually, this is micro-programming. You can actually go, so how do you design a machine? You design the data path, you design the control signals, and then you go fill out this table. For example, this is the finite state machine part for load instruction that someone designed. It's very similar to what we designed earlier, give or take a couple of things. This is the microsequencer someone designed. And now you go and fill out this table. This is your microprogram. These are your micro instructions. So this enables an abstraction, right? So earlier we had assembly programming. Now we actually control signals. But going directly from assembly to control signals, now we introduce some other abstraction, which is micro instructions, right? The hardware designer has this microprogramming abstraction. Now this way, the designer can translate any desired operation to a sequence of micro instructions. All the designer needs to provide is three things: the sequence of micro instructions needed to implement the desired operation, the ability for the control logic to correctly sequence between micro instructions, that's micro sequencing, and also any additional data path elements and control signals needed. If you already have the data path and control signals, you don't need anything. So if your data path and control signals are powerful enough, you can implement new instructions, new micro instructions internally. You don't need to tell anyone. And that's what brings us to this thing that we have looked at earlier, right? Remember, we had the semantic gap picture. You have high-level language, ISA with complex stuff, complex ISA, complex instructions, complex data types, complex addressing modes. These get translated into micro instructions in existing processors. So existing processors actually operate this way. A complicated ISA like x86 gets translated using this hardware translator micro sequencer that I kind of went over quickly to actually go through, translate every instruction to a sequence of micro instructions. And an instruction can be translated to many micro instructions. let me cover this slide and then we're going to take a break. Basically, there are other advantages to this. You basically can take an ISA and translate it to microcode and implement things in different ways. You can have a minimal data path to emulate the ISA. And you can think of this as a user invisible ISA, like we've been kind of thinking of it, right? This also enables easy extensibility of the ISA. You can support a new instruction by changing the microcode. Someone creates a new instruction, you basically try to figure out how to include it by changing the microcode itself. You can support more complex instructions as a sequence of simple micro instructions. For example, string copy can be supported as a sequence of smaller instructions. Even though you don't have a native string copy operation, you can change the microcontroller to actually do this. Multidimensional array updates can be supported. It also enables update of machine behavior. For example, if you have a buggy implementation, you have a bug in your processor, it gets discovered in the field. Some smart security person or some smart person discovers that there's a bug. You can basically fix that bug. You basically say, okay, this particular instruction is buggy. I'm going to execute it in a different way by changing the microcontroller, by changing the microprogramming. This requires changing the microcode, of course. This is called microcode updates. So you need to have a programmable microcode engine for this. Okay, this is where I'll stop. Let's be back when the bell rings. We're gonna continue with pipelining and a lot of ideas. If you have questions, let me know. Is everything good online? Okay. Okay, so now I've kind of covered the microprogram control relatively quickly, but this is really just for your benefit because I think it's a very nice and clean way of designing a system. You have a clean microcode and you can update it even after the processor is in the field, right? You can patch the microcode basically. So now you know what it means when, for example, a major company releases a microcode patch. What they're doing is they're really updating the micro instructions in that control store table, meaning they're updating how they process an instruction using these control signals, right? And the reason they can do that is not everything is hardwired completely. There is some layer of translation like this that enables them, that gives them some flexibility to translate from the ISA to micro instructions, and there's some programmability in this layer, essentially, right? And what we've kind of done is, when we actually were doing, determining the control signals for every state in the finite state machine, we were really microprogramming the machine. We didn't call it microprogramming, but it's really microprogramming the machine. You set the control signals, and somebody does that, and if there's a bug, they actually fix it, and they release a microcode patch, and you download it, and your processor works better, or more correctly, or high performance also in some cases. Okay. So essentially, the ability to update or patch microcode in the field enables ability to add new instructions without changing the processor, which is very nice because of that indirection that we discussed. Ability to fix buggy hardware implementation, ability to provide a mitigation for security concerns, for example, etc. And there are many historical examples of this. For example, early IBM machines had microcode stored in main memory, and they could update after a reboot. Similar things happened, and there are very nice papers that talk about it. IBM calls this millicode, and they actually describe how they do it in their Z-series processor. Z-series processors are actually pretty heavy processors. They're really huge. They're millions of dollars, and a lot of like big institutions buy them and use them for many, many years. And they may need to update the microcode many times over those many, many years. Okay, interesting thing in some processors where actually you could update the microcode while the processor is running. This is very similar to a program, right? A regular program, if you think about it, you program and you can change the program while the processor is running clearly, right? That's nothing new, but here, updating the microcode is really changing how the hardware behaves, and you can actually do that also. So it was a more user microprogrammable machine, and there are actually interesting papers on that also. And I already said that systems today use microcode patches to fix hardware bugs and issues. There's more. If you really want to learn about microprogramming, there's a longer lecture that talks about it, but I'm not going to cover it more here. But I'm going to ask the question, can we do better? Basically, we've designed some things, and we've designed the multi-cycle MIPS processor, and we designed the multi-cycle MIPS finite state machine, and we also said, even though your book doesn't handle multi-cycle memory access, we can also handle multi-cycle memory access very easily. So we can handle a lot of really realistic things relatively easily with this multi-cycle machine. So we're getting, compared to single-cycle machine, this is like heaven. Like you're really dealing with real things right now. Single cycle is kind of a exercise that you do, but it's going to be useful actually in what I'm going to say soon, which is pipelining. Okay, basically, can we do better? What limitations do you see with the multi-cycle design? I've already given you actually this, so I'll go through this relatively quickly. But basically, one limitation is hardware cost, of course. Hardware cost, unfortunately, we're going to add more and more hardware costs to the machines. Later, maybe in lecture 18 or so, we're going to look at paradigms where hardware cost will be reduced. But that will come at the expense of lower performance. So we'll have low performance. But limited concurrency is something we can fix by adding more hardware. So basically, if you have carefully followed what we have done, we added hardware resources. They're less than a single cycle machine, but we're not using those hardware resources all the time. Some hardware resources are idle during different phases of the instruction processing cycle. Depending on which state you're in that finite state machine, you're using only a small fraction of the resources. It could be a very small fraction, actually. So for example, fetch logic, the logic that you added to the data path for fetching instructions, is idle when an instruction is being decoded or executed or calculating memory address, etc. Fetch logic is used only when you're fetching instructions, right? Most of the data path is idle when a memory access is happening. You're just accessing memory, waiting. And everything else in the data path is idle, right? Even though those resources are there, they're waiting for the memory access to finish so that they could be used, okay? So basically, people ask this question, can we use the idle hardware to improve concurrency? Right? And the goal is to really get more concurrency, enable utilization of a bigger fraction of the machine. Essentially, what is more concurrency, right? More concurrency is you do more things at the same time, and this gives you higher throughput, higher instruction throughput. In other words, more work completed in one cycle. Okay, I think I give you the idea over here, but essentially, the idea of pipelining is very simple. When an instruction is using some resource in its processing phase, process other instructions on idle resources that are not needed by that instruction. For example, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode the next instruction. When an instruction is accessing data memory, execute the next instruction. When an instruction is writing its result into the register file, access data memory for the next instruction. This way, you can actually have many instructions in the machine at the same time, right? Does that sound good? Even better, but essentially, the idea is to potentially have, let's say, 6 instructions, right? It depends on how many stages you break this down to. So it looks kind of like this. When an instruction is writing its result, the other instruction is accessing, essentially doing ALU computation, another instruction is accessing the register file, another instructions maybe fetching, and also some other instructions updating data memory, which is not shown over here. So all these different colors are different instructions. But of course, we need to be a little bit more careful for reasons that we're going to study this lecture and in the next lecture, and maybe even in the next lecture after that. Does it sound good? Does it sound like it will enable better performance? It will, right? Because you're, as opposed to doing one thing at a time, only one red thing, you're doing many different things, colorful things over here, right? Okay, so let's go into pipelining. This is actually an idea that's used in, I'm going to show you a picture, factories a lot, right? You pipeline the processing or the construction of a part, a car, for example, or part of a car. And essentially the piece starts from somewhere, and then somebody does something to it, passes it along to the next person, and that person does something to it and makes it bigger, passes the next person, et cetera, and you pipeline the construction of the car. Today, robots do a lot of that, so robots actually pipeline the construction of a car. So essentially, systematically, we're going to do something similar, pipeline the execution of multiple instructions. The analogy is assembly line processing of instructions or in factories. The idea is we're going to divide the instruction processing cycle into distinct stages of processing, ensure there are enough hardware resources to process one instruction in each stage for whatever we're doing in that stage, and process a different instruction in each stage. Not the same instruction, different instruction, okay? And instructions consecutive in program order are processed in consecutive stages, okay? The benefit is this increases the instruction processing throughput. We define, for example, CPI as part of the performance equation. If you remember the performance equation, execution time is equal to number of instructions times average cycles per instruction times clock cycle time. How do you improve throughput? Forget about number of instructions. We cannot do much about it in the microarchitecture level. Clock cycle time, that's one way of improving execution time, reducing execution time. But if you actually process more than one instruction per cycle, you're really reducing cycles experience per instruction, right? On average. Because you're really overlapping multiple instructions at the same time, right? So you're really improving IPC, which is the inverse of CPI. IPC is instructions per cycle, CPI is cycles per instruction. Okay, so clearly there's a downside, and we'll start thinking about this, and we're going to see a lot of the downsides. One downside is going to be more hardware. Essentially, we're going to add more hardware to enable this sort of processing. And then there will be other downsides, as you will see. Does that sound good? Yes? Okay. I see some heads nodding. Let me give you the benefits pictorially, because a picture is worth 1,000 words maybe in this case. So this was multi-cycle. I'm assuming we do 4 cycles per instruction, 4 adds, for example, add operations. Each add takes 4 states or 4 cycles. Fetch, decode, execute, write back. And then you start the next add, fetch, decode, execute, write back. And then you start next add. You can see that we serialize the execution of 4 different adds in this case. When you do pipelining, this is what you do. While you're fetching while you're decoding the first add, you're fetching the next add. While you're executing the first add, you're decoding the next one, you're fetching the third one. While you're writing back the result of the first one, you're executing the second one, decoding the third one, fetching the fourth one. So it's kind of beautiful like this, assuming the instructions are not dependent on each other, which is something we will discuss. But you can see that our throughput has increased. We get 4 cycles per 4 instructions. In other words, we complete 1 instruction per cycle, right? And in the steady state, you can see that there are 4 instructions that are concurrently in the machine, right? The steady state means when the pipeline is full with instructions. This is the steady state picture. But basically, the key takeaway is you're completing 1 instruction every cycle, right? Whereas here, you're completing 1 instruction every 4 cycles, right? So that's the throughput improvement. So it improves your throughput. It improves your execution time in this case, and you can calculate the execution time improvement. Here it's 16 cycles. Here it's 4, 5, 6, 7 cycles, right? Okay? So it improves your instruction throughput, it improves your execution time. It doesn't improve the latency of a single instruction. A single instruction still takes the same amount of time, as you can see, right? Here, each instruction was taking 4 clock cycles, assuming clock cycles are the same in multi-cycle and pipelined, which may not be the best assumption, but we're going to assume that for now. They're close enough. Each instruction still takes 4 cycles in the pipeline machine, right? So we didn't change the latency of the instruction, but we improved the throughput of the machine and the execution time of the entire program by overlapping the execution of different instructions. So this is actually a critical distinction between latency and throughput. Your latency of an individual operation may not improve, but your throughput of the overall thing that you're doing in your program may improve by overlapping latencies of different operations that you do. So that's the power of overlapping latencies. Okay, so the question is, of course, is life always this beautiful? This looks beautiful. This is perfect pipelining, kind of, because we can do what I show you over here. This doesn't happen if the instructions are dependent on each other, for example. So we're going to look at when life becomes not as beautiful, and we're going to try to solve those issues. Make sense? Okay, so another book, the Hennessy and Patterson book actually has another analogy that I like, which is the laundry analogy, which you may actually empathize with. Laundry is a pipeline process, basically. You have a bunch of loads, and each load takes some time. You basically put them into a washer, and then into a dryer, and then you fold them, and then you put into the cabinet. Assuming each step takes, I guess, 30 minutes over here, you finish 1 load in 2 hours, right? And then you start the next load, right? Multi-cycle machine looks kind of like that. You wait until you finish the entire load until you use the washer again. This kind of doesn't make sense if you want to save time, right? Because you can start using the washer over here for the next load. Okay, so you can read this on your own. But basically, steps to do a load, a laundry load in this case, are sequentially dependent on each other. But there's no dependence between different laundry loads. Different steps do not require the same resources either. And a washer and dryer are completely disjoint from each other. Of course, you could have a washer and dryer that's put together. You can either do washing and drying, and there are machines like that, and those machines are terrible for pipelining. And they're actually not good for latency also. I have one, so I know. So it's good to have a separate washer and separate dryer, frankly. Specialization. There are multiple reasons, actually. You cannot specialize a washer and dryer to be as good as a dryer specialized for just drying. Very similar, actually, trade-offs happen in architecture. You design an ALU, you can much more easily design a adder that's specialized for addition, as opposed to adder plus multiplier that's good at doing both, right? Okay, anyway, I digress. So basically, this is what every one of you do laundry, right? How every one of you do laundry if you have 4 loads. Hopefully not. What you do is, basically, if you do this, you finish one load every 120 minutes or 2 hours, based on the parameters that I just described. But if you pipeline, which is what reasonable people would probably do, after you finish the first load and start drying it, you also concurrently do the washing of the second load, right? So you do 4 loads of laundry in parallel in the steady state, which happens to be over here in this case. Yes. And this way, you can start and finish one load every 30 minutes. So you increase your throughput by 4x, as you can see. Even though the latency of every single load did not reduce, latency of the entire 4 loads actually reduced significantly. Makes sense, right? It's the same example that I gave you. Instead of ads, now we have laundry loads. So, okay, I've already said all of this. No additional resources. In this particular case, you don't need additional resources. You may need slightly more amount of time to switch between one load to another, but that's the additional overhead that we're going to kind of see soon. Okay, in practice, that damn dryer takes always long, right? Who suffers from the dryer? Which one's the longest? Dryer, washer? Nobody does laundry here anymore. Robots do laundry. For me, it's the dryer. Dryer is always long, especially a high-performance dryer consumes a lot of energy and a lot of time. So you do one load every 150 minutes with that dryer, right? That dryer takes 1 hour, as you can see. Now, how do you fix this problem? This is essentially a problem that you have in real machines also. And multiplication takes long, for example, right? How do you deal with it? What this dryer has done to us is basically made our life worse for pipelining also, right? So as opposed to having one load every 30 minutes, now I have finished one load every 60 minutes because I have a slow dryer, and slow dryer is really my bottleneck, if you think about it. I cannot really start the second drying process until this first load finishes in the dryer. So your dryer is really the bottleneck, your execution, right? Okay? So how do you fix this problem? Anybody? Yes? Second dryer, okay. Okay, there are multiple fixes. Second dryer is one fix. Okay, I already said this. The slowest step, the dryer decides the throughput. Buy a second dryer. Dryer A, dryer B, alternate between them for consecutive loads. And this is something that you do in real life also. An adder A, adder B. Multiplier A, multiplier B. So the same concepts in life actually apply nicely to architecture as well. Now, this is one solution. The other solution is make your dryer fast, right? So spend a lot of effort to have a fast dryer. That's another possible solution. So either way, your cost increases. Your cost essentially increased over here, right? Okay. Okay, you basically restore the throughput using 2 dryers. Okay, this is just fun for you. These are automobile assembly lines. One of the main things this was tested on was a particular part. This is a Ford assembly line a long time ago, like early 20th century, maybe late, before everybody here was born, including myself. Yeah, basically they had this component that supplied ignition energy to the engine before generators became common, and they called this the magneto. It was a pretty complex and innovative component at the time, and they basically had to build an assembly line to assemble this component. I'm not going to go through anything over here. You can read it clearly, but you can read the numbers over here. On average, a worker could assemble 35 of them in a 9-hour shift, or roughly 1 every 15 minutes. So it's a throughput and latency thing over here. By moving to assembly lines like this, which is essentially pipelines, they were able to reduce the assembly time from 15 minutes to 5, and the required workforce decreased from 29 to 14. So with robots, you can do even better, probably. But I like Magneto for another reason. Does anybody know Magneto for some other reason? No? Nobody follows X-Men? Am I still too old? In X-Men, there's a Magneto. And it's inspired by this Magneto, actually. That particular device that's used in cars, early cars, inspired something in X-Men. Okay, anyway. This is more like a regular automobile assembly today. Okay, a real computer that had pipelining was IBM Stretch. This is actually in 1960s, and you can see that computers were a little bit larger at that time. Good luck carrying this in your pocket. And also a little bit more expensive, as you can see. But anyway, pipelining is real and it's been used for a while. Okay, now let's talk about what it means to have an ideal pipeline and how a modern microprocessor pipeline is not ideal. Essentially, our goal is to increase throughput with little increase in cost. But we saw that if you already have a slow component, you need to increase cost. In this case, we want to not increase the hardware cost. Also, you don't want to increase latency. We're going to talk about that as well. So ideally, you should be repeating the same operation many, many times, right? The same operations repeat on a large number of different inputs. For example, all laundry loads go through the same steps. Right? Ideally, your operations should be completely independent of each other. There's no dependencies between different loads in your laundry, for example, right? That should be nice. And ideally, you should be able to uniformly partition them into sub-operations. So you can divide processing into uniform latency sub-operations that do not share resources. Again, in the laundry example, we saw that we had 30 minutes for each step. That's a uniformly partitionable. But ideally, we would like to make it even more partitionable. We would like to have a 5-minute dryer. That would be nice, right? Okay. So, but doing laundry is not bad, actually. Assembly line is not bad. What about instruction processing cycle? We're going to talk about that. But let's talk about this ideal pipelining element. Instruction processing cycle. You have basically some combination logic. This is a single cycle kind of processor, right? You store the results in registers, essentially. This is your input register, this is your output register. They can be the same. But essentially, you have some combination logic. Let's assume that it takes t picoseconds to process some instruction. Throughput is 1 over t. We divide it into 2. Ideally, we would like throughput to be 2 over t, multiplied by 2. And we divide into 3, we would like 3 over t. Now, this is not that realistic because we cannot divide work nicely this way. What happens is when we actually look over here, there's some amount of useful work over here in the t picoseconds, and there's also a register, sequential logic delay. So when we actually try to divide t, even if we can divide t equally into k components or k stages, the register delay stays the same. You still need to latch things into a register at the end of a clock cycle. So your throughput is really dictated by this equation over here. T gets divided by k. That's also ideal if you can exactly divide it. But you cannot get rid of this s. This sequencing overhead or sequential logic delay is there. So ideally, if as k goes to infinity, this, let's say, goes to almost 0, maybe 1 gate delay, whatever it is. So your throughput maximum is really dictated by the sequencing overhead of the registers. So always keep this in mind. Register delay reduces throughput, and that's your limiter. Why don't we pipeline things to very small amount of combination logic? This is the reason. Well, this is one reason. Essentially, you get dominated by the sequential logic transitioning overhead, and most of your clock cycle gets wasted on essentially putting things into the register and taking things out of the register, as opposed to doing useful work in computation of an instruction, right? Okay, this picture still assumes perfect division of work between stages. We're going to get back to that. You may not be able to perfectly divide t over k, right? Because you have granularities of processing, like accessing a register file, accessing a memory, doing something in the ALU. You may not be able to perfectly pipeline all of them, right? Okay, cost. Cost is also interesting. Basically, if you look at a non-pipeline version with some cost, you need G gates to implement things. You also need some register cost, G plus R. As you pipeline, perfect pipelining assumes you divide G by K. And you don't increase the combination logic. We're going to see that that's not true. But even if that's true, you need more registers. So you need to multiply the register cost by K, at least linearly. Maybe it's not exactly. But registers essentially increase hardware cost. You need to add pipeline registers at the end of each pipeline stage. Okay? Okay, this still ignores the fact that you may need to actually replicate resources and also some registers. But register cost dominates if you pipeline too much, essentially. Hopefully this makes sense, right? This is why people don't pipeline too much, let's say. If you could actually pipeline a lot, maybe we could have like 50 gigahertz processors by now. You could get that potentially, but you would increase frequency. Your cycles per instruction would be much worse today if you do that. Okay, now let's go into a little bit more detail. We're going to do more pipelining, and you've seen this many times. That's why I'm going through this relatively quickly, just to jog your memory. We have an instruction processing cycle, and we're going to essentially pipeline it. This was our single cycle microarchitecture that we developed in an earlier lecture, not the multi-cycle. So I'm going to actually start with a single cycle microarchitecture. As I said, there is a good reason to teach single cycle microarchitecture. One reason is to show you that this is a bad idea. It's always good to show bad ideas also. The other reason is it actually enables a good educational purpose to transition into pipelining, because a lot of what you will see in the single cycle will be very similar in pipelining also. The control logic, control signals are actually going to be exactly the same. But if you look at the pipelining over here, this is our throughput, 1/t in a single cycle, right? This is one way of pipelining. So we basically add registers somehow. We need to do some register, right, etc. But let's assume that somebody divided the stages like this, right? And ignore these back edges for now. Those back edges are always problematic in pipelining, and you need to be very careful, because there may be there's another instruction over here, right? There's another instruction over here. The different instructions are in different stages. So you cannot just take something over here and put it into the program counter, because it affects the other instruction that's over there, right? Now you need to think about the hardware as catering for different instructions in different stages. You need to be very careful what you do when you actually cross different stages, right? If there's a line that crosses different stages, you should be very careful. Okay, anyway, basically, instruction fetch is 200 picoseconds, decode is 100. This is 200, 200, 100. Okay, right back. So these 5-stage pipeline, somebody designed it. It's not a perfect design right now. We're going to build it later on in some way. Is this the correct partitioning? This is always something that you can ask. Maybe that's not the correct partitioning, right? Maybe you need a 6-stage pipeline. Maybe you need a 4-stage pipeline. Why not choose different boundaries, right? This is always a problem in pipelining. We're not going to talk much about this, but keep this in mind. When you're designing a pipeline processor, you need to make some choices, and there are no easy choices in a sense. But let's analyze this design earlier that we have in this picture. So if you assume that these are the instructions that I have, different loads completely independent of each other. If you don't pipeline, and if you somehow design a processor that takes, let's say, single cycle, you need 800 picoseconds for this load, 800 picoseconds for this load, 800 picoseconds for this load, okay? Because register file is only 100 picoseconds to access. When you pipeline, every stage needs to take the same amount of time, because you move one instruction from one stage to the next stage in consecutive cycles. You cannot have different stages taking different cycle times. That breaks the clock cycle time. In this case, you see that this load takes actually 1,000 cycles, right? 1,000 picoseconds, sorry. 1,000 picoseconds to complete, because it goes through 5 pipeline stages, and each pipeline stage is 200 picoseconds. So even though instruction, this didn't need 200 picoseconds completely, it only needed 100 picoseconds, you still need to ensure that you spend a full clock cycle in this pipeline stage, okay? And the next instruction is also similar. So what happened here is our throughput increases. We have one instruction every 800 picoseconds previously. Now we have one instruction every 200 picoseconds. But our throughput is not perfect, meaning we pipelined with 5 stages. If it was perfect pipelining, we would expect a speed up of 5x, right? But we have a speed up of 4x in terms of throughput. Well, because we wasted some of the clock cycles, right? Basically, half of the clock cycle is wasted in 2 stages. Whenever you're accessing, is essentially in the decode and register file access stage over here, and the write back stage. Make sense? So basically, you don't perfectly partition work in general. There's no easy way to solve this problem also. And as your pipeline stages do more work, are not balanced, so this is called balancing the pipeline. If your pipeline stages are not perfectly balanced, meaning work is not perfectly partitioned across stages, you will not get the ideal speed up. So this is a first immediate hit at our pipeline, let's say. We expect 5x speed up, we get 4x. It's not that bad. If you actually pipeline more, maybe you'll get a little bit more, but you will not get the ideal. Okay? We're going to see more and more hits to the pipelining, and we're going to try to solve those. Okay, so if you want to enable pipeline processing, you need to add pipeline registers, right? So this is a stripped down version of a single cycle processor that we have seen earlier. Meaning you need to do what I show you at the bottom over here. So this is a pipeline version of the single cycle or the basic single cycle processor. Basically, you fetch the instruction, you increment the program counter. We keep this nice incrementing program counter over here as opposed to multi-cycle, because this helps pipelining actually. And then you store the intermediate results in this instruction fetch, instruction decode pipeline register. We're going to call these pipeline registers. And then the decode and register file access does something, and you store the intermediate results over here. And then the execute stage and the branch calculation stage does something, and you store the intermediate results over here. And then the memory access stage does something, and you store the intermediate results over here. And then the write back stage does something, and you store the result in the register file, etc. And then there are also arcs that go this way, as you can see, arrows that go this way. This is basically to change the program counter. The branch finishes execution over here, and the branch condition is calculated, target is calculated, they're stored in this register. In the next cycle, if the branch is supposed to be taken, you change the program counter to the target address. Although those paths are not shown over here, but you need those paths to execute the instructions. But the key takeaway over here is that if you want to pipeline the processing, you need to have pipeline registers to enable one instruction to be fetched, store its result, while another instruction is being decoded to store its result at the end of the cycle, while another instruction is being executed, and while another instruction is accessing memory, while another instruction is writing back to the register file. Make sense? So we added these registers. These registers also kind of exist in the multi-cycle in a different way. Okay, here you need to think differently, because what we're doing is we're pushing new instructions into the pipeline. In multi-cycle, we still have single instruction to process. Okay, so for example, these are some example registers. You have some instruction register. You have PC+4 over here. You have registers that you've read. You have the immediate over here. You have the ALU result. You have one of the registers. So whatever registers that you're going to need later, you need to keep in your pipeline registers. For example, PC+4. PC+4 is needed here. Why? Because we're going to calculate the target address of the branch by adding a sign extended left shifted immediate to it. And this is the next PC of the branch, as you can see. There needs to be also a branch condition that says stored. This is not showing the entire picture. But these are the things that you need. You need data elements that are required to process the instruction later in the pipeline stages. And you need to propagate them across these pipeline registers. So we will later see control also. You need to do the same thing for control. So these registers can become quite large. Make sense? Okay. So of course you need to make sure no resource is used by more than one stage. While you're reading the registers, you should make sure nobody is updating the registers. That's going to be an important concern for us later on. Okay, so basically each stage is kind of exclusively reserved for the instruction that's being processed in that stage. Okay, so also all instructions classes must follow the same path and timing through the pipeline stages because of this design, right? So for example, you fetch the load. At the end of the cycle, you store whatever you need to store, PC+4 and the instruction register, etc., some control signals maybe. And then load goes to the decode. And in the next cycle, you do the processing over there, store the results into the next pipeline register, execute next pipeline register, and memory next pipeline register. And write back, you write it back to the register file. Okay, so something's happening here. Even though a load actually is a good example, because load goes through all of the 5 pipeline stages. But if you're doing, for example, an add, you don't really need the memory state, right? But add still needs to go through the memory state, right? Because it's a pipeline. And this pipeline just, you cannot just bypass, because if you bypass, there's a lot of complexity that's added. You could actually bypass in very advanced designs, but not in classical pipelining. So basically, this has a performance impact, meaning an instruction goes through some pipeline stages even though it doesn't need it. It basically consumes some cycles per instruction, right? Essentially. It's very different from the multi-cycle design if you think about it. In the multi-cycle design, an instruction takes as few states in the finite state machine as possible, right? That's the ideal design choice. Here, every instruction takes the same number of stages in the pipeline. But it's not as bad as single cycle because single cycle is insurmountable as we've discussed. Right? Okay, so this is in a pipeline operation example. You fetch the load and then you fetch the subtract, for example, and then they flow through the pipeline kind of like this. I'm showing you two instructions, right? Now it's nice. While load is doing memory access, subtract is doing execution. While load is writing back data to the register, subtract is going through the memory stage doing nothing because subtract doesn't access memory in the memory stage. And load gets out of the pipeline after it's done, and subtract goes to the write back stage and writes its results. So hopefully this makes sense, right? Basically, you fetch one instruction per cycle, and every cycle an instruction moves from one stage to another stage so that other instructions keep coming into the pipeline. So I kind of shown you every clock cycle over here. Clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4, 5, 6. These are simple concepts, so hopefully this is simple. We're going to get to the more complicated concepts like, is life always this beautiful? Meaning, what if that subtract was dependent on the load, right? What if that subtract needed the value produced by the load? Then it cannot keep going, okay? We're going to get to that. But let me give you an operational view of the pipeline also, because this is kind of fun to think about. So these are different time units, time 0, time 1, time 2, time 3, time 4, time 5. This is instruction 0 doing fetch, instruction fetch. At time 1, there's some concurrency. At time 2, 3 instructions are in the pipeline: fetch, decode, execute, as you can see. So basically, you can fill the pipeline. This is called the steady state of the pipeline. And you keep basically filling new instructions into the pipeline, as you can see. Instruction 0 is the oldest instruction. It finishes after it does write back. Instruction 1 is the second oldest, third oldest, etc. So you can see that we are assuming a 5-stage pipeline here that's divided similarly to what I've shown you earlier. And this is called the steady state, meaning this is where your pipeline is full. All of the stages have an instruction in it. And once your pipeline is full, that's good. You have the highest throughput at that time. This is what we would like ideally. Your pipeline always full, and you keep being full just like in this picture. But life is not going to be this beautiful. So this is an operation resource view also. If you look at the different stages over here, fetch, decode, execute, memory, write back. And if you look at the time over here, this is how the instructions flow. Again, this is just for you to think about. Some of this is actually used for formalizing the pipeline and actually building the pipeline, etc. But I'm not going to go through that in this course. So you can see that instruction 0 kind of flows at different time units to different stages. And this is where your pipeline is full, and all of these cycles, T4 through T10, are very useful for performance. Okay, let's talk about control points in a pipeline. This is where the single cycle is actually quite useful. You basically take the single cycle design, and you have the identical set of control points as the single cycle data path, except you have some more registers, the pipeline registers. So this is actually very similar to the single cycle processor we designed, except it has these pipeline registers also. This is a 5-stage pipeline: fetch, decode, and read registers, execute, memory access, write back. And you have 4 pipeline registers in between stages. But the control points are exactly the same as the single cycle data path, and you can confirm this on your own if you would like. So what do we do with control in a pipeline? For a given instruction, we have the same control signals as the single cycle processor that we designed earlier. But we don't use all of those control signals at the same time, because as a single cycle processor, you have a single cycle. You use all of those control signals. They're distributed to everywhere at the same time. Here, control signals are required at different cycles, depending on the stage. So you have the same control signals for a given instruction, but you use them at different cycles. If the instruction is in the fetch stage, you use some control signals. If the instruction is in the decode stage, you use some other control signals. Make sense? So how do you do this? Basically, one thing you could do is you could decode an instruction once using the same logic that we use as single cycle and buffer the signals until they are consumed. And this is what things kind of look like. This is, again, an abstract view over here. This is the fetch stage. You know the instruction after the fetch state. There's some decoding that happens in the decode state. And this is where you generate the control signals, if you remember. these control signals can be generated for all of the downstream stages. These are the control signals that I'm going to need in the execute stage. These are the control signals that I'm going to need in the memory stage. And these are the control signals that I'm going to need in the write-back stage. So I generate all of those control signals as much as possible, of course. Some control signals may not be easy to generate because they're dependent on processing, as we've discussed, like the branch condition. Ignore those. Whatever you can generate based on the opcode, you generate. You put them into the pipeline register and designate where they're needed, maybe, and then use them when they're needed. So these control signals that are only needed in the execute stage are not needed in the memory stage. You don't need to propagate them into this register that's between execute and memory stages. And these control signals that are needed only in the memory stage and not needed in the write-back stage, you don't need to propagate them to the pipeline register between memory and write-back stages. Okay, but the control signals that you generate are the same as the single cycle control signals. You just delay when you use those control signals because of the definition of pipelining, right? An instruction does something, a part of the instructions processed at different cycles, and different instructions are processed on the same hardware at different places. Okay, this is not the only option, but you could also have another option, which is instead of decoding all of the control signals that you need ahead of time in the decode stage, carry part of the undecoded instruction, let's say, instruction word or field, down the pipeline and decode locally. So basically distribute the decoding to happen locally across later stages. Clearly, there's a benefit to that. That way you don't need to store all of these pipeline registers. You basically trade off sequential registers with combinational logic. But we're going to assume kind of the first option for the rest of the discussion. But the second option is equally viable. Okay, which I kind of gave you the answer. It depends, basically. So here, this is actually from, this is actually the same single cycle processor divided into pipelines, and the control signals delayed as to when they're really needed. For example, the execute stage needs a LU source, these multiplexers over here. They need to be controlled. And these control signals are generated in the previous cycle, stored in the pipeline register, and used in the next cycle. These are the control signals that are needed in the execute stage. Memory stage, some controls, like branch, whether this is a branch, is needed because we calculate the branch condition in the previous cycle, like that's 0. If the branch condition, if what we're processing is a branch, and the branch condition is satisfied, meaning it was 0, then we basically set PC source to 1, which means that we get the PC from the target address that was computed earlier, right? So there's no magic. We've actually built all of this data path. The data path is already there. We just delay the control to the appropriate time, right? Does that make sense? Okay, this may require some more thinking and going through the figures, but essentially, this is your single cycle processor divided into different stages, control signals delayed to the appropriate place. So let's take a look at memory also. Mem-write signal, for example. This mem-write signal is generated if the instructions are stored. And it's stored over here in the pipeline register. The store instruction moves that signal. That signal is moved to the next register. Store instruction calculates its address over here. And then that address is used to write some data value that's also latched by that store instruction in the previous cycle into this register. And in the memory stage, the store instruction uses the address that's latched, the data that's latched, the mem-write signal. Mem-read is, of course, 0 at that point, if you remember this signal, and then basically writes to memory. Okay? So while store instruction is moving from fetch to decode to execute to memory stages, necessary control signals are also being propagated with the instruction. Okay? But the data path is very similar to what we've designed. The data path does essentially the same things, except it does in different cycles. Okay, so this is one example over here. This is for the register write signal. Okay, essentially the register write signal needs to be propagated so that you write to the register in the write back stage as opposed to earlier stages. Okay, tomorrow we will pick it up over here. We'll go into a little bit more depth, and then hopefully we'll finish pipelining. I'll see you tomorrow.